Good afternoon, this is Mr. Schweitzer, and this is a first attempt at a video for Big Idea number 1. Big Idea for Advanced Placement Chemistry, and the chemical elements of our fundamental building blocks of matter, and matter can be understood in terms of arrangement of these atoms. These atoms retain their identity in chemical reactions. So this PowerPoint isn't as much designed to teach as to, I guess, reteach, or just to bring up some concepts that you need to focus on or get some help with, or just revisit. So here are all the enduring understandings, and I'm not going to walk through them directly, but we basically have atoms are made of atoms. All matter is made of atoms. So atom is a whole item. That's an important opposite right there. Atoms of each element have unique properties. So we're looking at the electrons versus the nucleus. This is periodic trends, probably the largest source of questions on the AP exam. Atoms are so small they are difficult to study by atomic models are constructed to explain the data. So we have means of people studying atoms that are very tiny, and we'll talk about a couple things I could put in there for that, like photoelectron spectroscopy and various things. Atoms are conserved in physical processes structured to explain experimental data in all collections of atoms. So either way, let's kind of roll through this PowerPoint here. First of all, the nucleus, number of protons, atomic number, determines the element. So this is important things about the actual nucleus. All the mass is located in the actual nucleus. A few things you might want to know here is that the mass number represents the mass of a single atom. So for example, if we were to put down, let's say, let's go with iron Fe, and let's say we have a number 56 here. Well, or it might go Fe-26. This 56, correction on that, 56. Because iron has 26 protons, you can say for certain that this big number here is the mass numbers, protons and neutrons. So in this case, this guy contains 30 neutrons and 26 protons for a mass number of 56. Of course, in nature, different atoms of iron contain different number of neutrons. So each individual isotope can have a very different mass. So the naturally occurring units of iron, based on their weights, has an average of, on the periodic table, 55.84. This is either AMU's, atomic mass units per atom, or we could say that, okay, this is grams per mole. So we picked out the unit mole to match up nicely with the grams. Alright, next up we have the electron cloud. So this is where all electrons are located around the outside. One thing I kind of mentioned to people about the nucleus versus the outside is Rutherford's experiment, where he took basically a piece of nuclear material and shot alpha particles at a gold foil experiment. Looks kind of like this maybe. And as he shot them through, he realized that, okay, that most electrons went straight through. Some got reflected back to detectors all over the place. And that being said, he came with the idea that essentially the nucleus is a very small, center, hard object with lots of space sort of around the outside. But when bonding occurs, of course, we're looking at these outer electrons, which are valence electrons. The number of valence electrons are pretty important to know how many. Usually match up with the family of the periodic table. Electron configurations, again, we'll just show an example or two here, but the orbital, quantum numbers are n equals the energy level. We have L, small l would be considered the orbital. Of course, an S is a sort of a sphere looking. P it's got some lobes to it. The suborbitals, you want to know those. These are dropped from the AP exam, but any college you go to, they will have these numbers that designate these suborbitals. The spin is, again, a characteristic or way of designating an actual electron in a suborbital. We have Hund's rule, which states that electrons, when you're doing an orbital diagram, will spread out as much as possible in an orbital. We have ground state versus excited state. Whenever we're doing electron configurations, we're almost always doing the ground state. It's possible to do a configuration for a higher state, but it just isn't as practical, so we usually just do ground state. This is an example of light being produced as electrons get shoved up to a higher energy level and they drop back down and give off a photon of light. So the energy in and then emission, it goes up to an excited state, comes back to a ground state, photon gives off. Not something we're really dealing with right at this moment, but it is something that is around the electrons. Electron configuration example, again, this thing is not full, so if I were to draw a orbital diagram about this, it would look like this. Again, I'm just showing this particular orbital. Arrow up, arrow up, arrow up, up, down makes no difference. But when they're in the same orbital, they must have opposite spins, and therefore this one will go down. And it could be either one of them. This could be anywhere. So this has two unbonded pair of electrons. And again, there are more orbitals and electrons here, and they could get excited to higher states. We call that the excited state. But again, we usually just do the ground state. The Pauli exclusion principle basically states that no two electrons in an atom can have the same quantum numbers. And like I said, this is dropped from the AP exam, but if you have an electron in the first energy level of an s orbital in the s suborbital with a 1/2 spin, then these are the four numbers that would describe a particular electron involving the four quantum numbers. And no two electrons can have these same numbers in the same atom. So, periodic trends. Okay, so this might be the most, again, tested part of big idea number one. Make sure you know the trends. Trend would be atomic radius, ionization energy, electron affinity, electronegativity, and you should basically know what they are. So let's move on. So Coulomb's law is justification for many of the trends. We never calculate anything with this, but keep in mind positives and negatives attract, positives and positives repel, just like negatives repel. So this might be the positive of the nucleus, the entire nucleus. This might just be the negative of an electron. So electrons don't pile up. So usually, unlike the proton nucleus, which gathers, electrons, you just the charge of an electron. Keep in mind it's also distance squared, so as I get a certain distance away, then the force between drops by a quarter, or to a quarter. Atomic radius, okay, so what happens if you add a proton? Again, using justification here, we have protons and electrons. Adding a proton, the numerator will just cause this to increase. Increasing positive charge increases the force of attraction. Here are some examples. We have which atom is bigger here. Of course, increasing the traction, increasing the force of traction would cause the electrons to be pulled in towards the center of the atom. So keep that in mind. Which one's bigger? Now notice these guys here both have the same number of electrons. They're both isoelectric with neon, which has 10 electrons. So in this case, really they're the same number of electrons, just different number of protons. So since fluorine has, fluoride has more protons, it will be smaller than oxide. Again, notice that these have the same number of electrons. Fluoride just has more protons. All right, what happens if you just add a proton? Okay, here's my answer to the last one. Fluoride is smaller than oxygen. Okay. Next here, atomic radius. What happens when you just add an electron? Use Coulomb's law to justify. Okay, so again, electrons are negative. So when I have a positive nucleus here and I'm adding electrons around the outside of this thing, they don't like each other, so they tend to repel each other, push away. And so we're always going to get bigger. Always going to get bigger when we add electrons. But if we added enough electrons that the energy level is full and we open up a new energy level, then it's going to get significantly bigger. So we always want to be aware of how many electrons an atom has and have we gained or lost an energy level relative to electrons. So in this case, we have oxygen versus oxide. We gain 2 electrons. Again, this is isoelectric with neon. So it's just full at this point. We aren't opening up a new energy level. So oxygen is going to be smaller than oxide because we add 2 electrons in the same energy level. Here we have potassium versus K plus ion, potassium ion. And keep in mind that potassium only has 1 valence electron. So when we lose that electron, we lose in a whole energy level. So potassium is much, 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 much smaller than K plus because we lost an energy level. There is my answer for that particular questions. And again, of course, they repel. They are bigger because of the repelling force of Coulomb's law, Coulomb of repulsion. What happens if you add a proton and electron? So really we're adding this and this. So again, because of the numerator and mathematically, it's just going to increase. Increases the force of traction, and of course this just starts pushing things in, and we get smaller and smaller and smaller. This is mimicking just sort of traveling down the periodic row. As you add more and more protons, you get more and more traction. You got a nucleus in the center, electrons we add to the same energy level around the outside, and as you add more protons, it just gets pulled in tighter and tighter and tighter and tighter. It's a very gradual tightening, but nonetheless it is getting smaller. Of course, if you add a proton and electron, that allows you to add another proton, but another whole energy level, this is going to cause an increase in size. So sulfur versus chlorine, of course, whenever you have these problems, look and see where they're located. Sulfur and chlorine are right next to each other. So going to the right, I'm adding more protons, more electrons, but really we say more protons. By adding more protons increases the Coulomb attraction, therefore makes it smaller. So one way we describe that is called, I'll put that right here, the addition of protons, effective nuclear charge. Meaning that it's smaller because we're adding more protons and there's more effective nuclear charge reaching the particular outer electrons and all electrons. Argon versus potassium. Of course, argon is located right here. Potassium is located, in one energy level lower, all right? And all there is difference here is 1 proton and 1 electron. But since, again, we added an additional energy level, then this potassium is going to be significantly bigger than the argon. Sulfur is the bigger one, barely, and potassium is the bigger one here. Here is the answer to that particular questions. And notice that I have potassium being much, 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 much bigger because of the addition of an energy level. Overall trend, keep in mind that things trend-wise increasing in size. It decreases to the right, decreases as you go up, so it increases as you go down, adding energy levels. It increases to the left as you remove protons, removing effective nuclear charge. And the biggest atom here isn't even listed, which would be F, would be francium. Again, you cannot use the periodic table for justification of a trend. You could use it to just reaffirm your own thoughts, but then Coulomb's law is the governing basis. All right, ionization energy, this amount of energy needed to remove an electron to separate a negative from a positive. Anytime you're taking a positive, which is creating a magnetic or electric field, and you're taking a negative and you're removing it away from a positive, you must add energy into that process. You are doing what's called work, and work is basically a form of energy. To pull it away, you must invest energy. Conversely, to bring it in closer, then they naturally attract, and energy would be then given away. So in this case, to remove an electron is energy, needs energy, and we sometimes refer to this as exothermic or endothermic. Justification of Coulomb's law, for the most part, all we're doing is removing an electron. So this is my negative charge, this is the positive charge of the nucleus. solely based on the distance between them. Again, using Coulomb's law or effective nuclear charge to describe the positive attraction to the nucleus based on a certain distance away. Alright, so we're just going by size. Potassium versus argon. Of course, argon is significantly smaller. It's one energy level smaller. So to remove an electron from argon is significantly more difficult. So potassium has a smaller ionization energy than argon. You don't want to get caught up in the trap of saying, oh, argon's a noble gas, it's more stable, it's happier. Never want to say that. You'd want to say, well, its electron is closer to the nucleus. Therefore, it has a larger Coulombic attraction and more difficult to remove. Potassium versus argon, these guys are right next to each other, and potassium is going to have a larger, smaller ionization energy than calcium. Why? Because, well, calcium is smaller, ever so slightly smaller. And then again, oxide is slightly bigger than oxygen because of the addition of electrons. So it would have, because it's bigger, electrons a little farther away, it takes a little bit less energy to remove it. So the smaller atom here is on the right side. Smaller atom, smaller, 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 and they have therefore larger ionization energies. And then here is my answer to that. Next up, we have the trend for ionization energy. It just mirrors that of radius. Electron affinity is how much energy is released when you bring an electron closer to a positive nucleus. Remember, positive negatives naturally attract, so no energy needs to be invested. Here, in fact, energy gets released. So generally, we think of this as being exothermic. Again, here we have a unique informational thing where we have a chemical reaction representing the removal of electrons. So it's very important that we understand that this is ionization. If you ever need to write an ionization equation, this is it. Before picture, after picture, there's electron that lost. Before picture, after picture, the electron that's gaining. This is electron affinity. This is also known as oxidation, and this is also known as reduction. Alright, so looking at this, atoms are so small, difficult to study. Atomic models are constructed to explain experimental data and collections of atoms. I'm just going to go through a few different things that I think could be applicable to this particular enduring understanding. So we're looking to examine things. One thing we use is spectroscopy. So in this sense, we use light to shine through something. We refer to this as Beer's law. Beer's law is a form of spectroscopy to identify something with light, in this case a concentration. You should be very familiar with the Beer's law plot, concentration versus absorbance, or percent transmittance. It would be reversed, the line would be different, but either way, although not real common, you should note that the formula is absorptivity constant times the base path length times the concentration of items in there will give you your absorbance. Percent transmittance, obviously something that is opaque would have a 0% transmittance. Something that's very much clear, like go through, would have a 100% transmittance. Okay, moving along here. Another form of spectroscopy might be, okay, as mentioned earlier, you apply energy to something, it bounces up, electron bounces up at energy level. When it falls back down, it gives off a photon of light. You'll see the picture here. You might use this energy that comes in, would be infrared, and of course it has a certain amount of energy which allows the electrons to resonate or to flip back and forth between energy levels, giving off photons of light that are characteristic of the actual atom themselves. This is a way of identifying an atom. In college we use infrared spectroscopy all the time, and basically you would put in a known sample and you'd apply an infrared energy to this thing, and then you'd watch for, the machine would watch for the photons that are being released, and you get like a spike that would, and certain spikes of electrons that are jumping around, and then you test an unknown. You might have lots of things in the unknown. You get a certain spike here, a certain spike here, and all of a sudden you get this guy and another one. So this might clean that up a little bit. You'd use the fact that maybe this spike is the same as this spike. This spike is the same as this spike. and you'd maybe be able to identify the actual substance based on the spikes. This might be some other impurity. A flame test does the exact same thing, except we're using a Bunsen burner generally or some heating element, and therefore it gives off light of a different energy in equals different movement electrons, which equals different waves of light. Energy in generally is going to equal at some point energy out. Photoelectron spectroscopy. A couple things about this. Is relatively new for this thing. Keep in mind that we basically have ourselves an atom with the nucleus right here, and electrons are just basically piled in here. This would be my sort of my 1s2. Then we might have like a 2s2, and then we have the third energy level. We have the 3s2 and a 3p6. So as energy comes into this thing, it knocks out electrons. So the energy in equals the amount of energy it needs to dislodge. Now I'm going to just pick out one of these electrons here. Comes in, knocks one of these guys out, and then so there's a certain attraction to the nucleus, and this would be the energy of ionization. Plus, then whatever energy is left over would be translated into kinetic energy. So plus the kinetic energy of that particular item. So if you know the energy in and you know the ionization energy, you can take the kinetic energy and measure it, and it will show you the difference between the two. Will give you the energy. Well, if you can measure the kinetic energy, you know the energy in, then the difference between these two will give you the energy of ionization. So as I apply energy to these things, then they'll have a myriad of different ways of asking these questions. But generally speaking, you see your first spike would be like right here would be your 1s2. It has your most energy because it's the closest to the nucleus by Coulomb's law. And you notice that the energy increases this way. We don't really care about the energy as much. We're just comparing patterns. And then you'd see that the height of this thing represents essentially 2 electrons. And then you see another spike come a little later would be, well, hold on one second here. Let me erase that. Another spike would be similar in size, would be your 2s2. And then you might have another spike come along that would represent your 2p6. And then if you had another one here, it would be like your 3s2. And right now they're just comparing different electrons that are very similar electrons, the same electrons in 2 different atoms. And you'll note that this one is a little bit higher because I have more protons in an oxygen atom. Therefore, the Coulomb attraction to that same electron would be a little higher. And that's why it goes a little bit more to the left, because it's got a little bit more higher energy-wise than the nitrogen does because of more protons. All right, so atoms are conserved in physical and chemical processes, chemical reactions, in a simple rearrangement of atoms, no atoms are gained or lost. So basically, Dalton's law of definite multiple proportions and stoichiometry. So here's an example of a typical stoichiometry problem where they may give you pictures and you pick the picture out, or maybe in a written section they have you draw a picture. But note that we're doing H2O2, so sizes of these things are important. Hydrogens would be relatively small. Limiting and excess reactants would be also very important. So I would have to basically break these up here. 1, 2, 3, 4, 5, 6. I would have 6 little hydrogen atoms, and I could draw them in here. And they're not very good drawings, but I have 6 of them here. And I would only have 1, 2, 3 of the oxygen atoms. And that's it. So be aware of sizes of atoms and limiting excess reactants. Make sure everything's included. All right, so there's that picture. I could just moved it. All right, another example of keeping atoms whole and keeping track of them is going to be gravimetric analysis. Now, what this is basically saying here is I have 10 milliliters of this, and it takes 20 milliliters of this guy. You can read through it. They're both 0.1 molar, 0.1 molar. And I precipitate all of this stuff to get this stuff here, the solid. Note that they're same concentrations. I should say this is 20 milliliters of 0.1, and they don't give us the concentration of the AgNO3. They want us to figure it out. You can use stoichiometry this to figure out the moles of this using molarity equals moles per liter, and you find your moles of NaCl, and at a 1-to-1 ratio, how many moles would we have moles per liter of the AgNO3? Well, it's in half the volume, so it's twice as concentrated. Or just look at it proportionally wise. I have used at 1-to-1 ratios. Okay, I have twice the volume, so the same number of moles are in each. So since it's half the volume, this would be a 0.2 molar, twice the concentration. So here's the answer for that. You can look at it as a proportion, which is always great, or you can do the math a little more intense. And again, as always, we have this idea of a titration, which is tracking atoms. Just want to make a brief reminder of that as well. Finally, looking at a couple things here, empirical formulas versus molecular formulas. So again, atoms, molecules come in whole packets. So for example, CO2 and oxalate both have CO2 as their empirical formula, minus the electrons here. So they would have the same percent mass carbon, same percent mass oxygen, but they're different substances. Okay, keep in mind also that ionic compounds are always empirical. So NaCl is representing the bulk crystal of cations, anions, cations, anions, and forming this bulk crystal of cations and anions, always using an empirical formula to describe that. So I'm going to pause here for this particular video and then pick up the second half. Alright, so here we're looking to go over some examples of big idea number 1. Question-wise, we have complete combustion of a sample of hydrocarbon in excess oxygen produces equal molar quantities of carbon dioxide and water. So we have a combustion reaction of some hydrocarbon, carbon plus hydrogen plus O2 yields carbon dioxide and water. Just an FYI here, we have equal quantities of these guys as this guy. So that means for every 1 carbon, we have 1 water, but there's 2 hydrogens in here, so we have H2. So it's a 1-to-2 ratio. In that sense, we're looking for this to have a 1-to-2 ratio. Only one that could fit this would be this guy right here. Moving on, again, there's the answer. We have, in this case, zinc is used to reduce other compounds in chemical reactions if a chemist needs a substance that's more effective in reducing ability, which the following species is the best choice. Now, again, under this situation, you really got to be aware that what metals and nonmetals do. If you go back here, you'll see that, if we draw a picture of the periodic table, one of the most fundamental ideas in chemistry is that metals oxidize to form cations. So a metal will go to a cation and give away an electron. So this is called oxidation. So metals oxidize to form cations. So in this list, there's only one thing here present that can also do what zinc does, and that is sodium, because it's the only one that can yet oxidize. Every one of these guys have already been oxidized, well, at least these two, and this guy is a non-metal and isn't likely to go back to chlorine. Again, that would be oxidation, but chlorine is chloride's much more stable than chlorine. So other way, it's happy where it's at, or so it's low energy. This is a problem here where, again, looking for the wrong answer as well as looking for the right answer. So here we have 2 items, Te and I. They are right next to each other on the periodic table, and this guy has an average atomic mass of 127.6. This guy is 126.9. So one unique situation where this guy is actually a little heavier on average. So again, we're looking for ratios of masses of neutrons. So addition or subtraction of neutrons has nothing to do with the electrons coming and going. Again, no addition of electrons coming and going. So we're down to these 2. Again, we're only really worried about the Earth as far as Te being more abundant in Earth. it has nothing really to do with how much TE is available on Earth or anywhere. It's saying of the TE present, how much of it is one version, how much is another version, how much of it is something else. And so we're down to the last one, C, which is the correct answer. Iodine only consists naturally occurring isotope is 74 electrons, neutrons, whereas TE has more than one isotope. So you're seeing a bunch of versions of TE, and the question is asking which of the following could justify that this thing is, which would be the best basis for concluding that is a pure sample of TE. We're missing one here involving iodine. So, what is the best reaction represented by combustion of hydrogen and water? Okay, in this case, the answer is this guy. Of course, we're looking at sizes of atoms, diatomicness of atoms, and of course the stoichiometric ratio. There is no excess, so there should be no excess here. Check that out. The mass percent carbon pure glucose. I think this is an easy question, but it's more difficult if you don't see it right immediately. They're looking at, in this case, go to the answer here, a substance that could be mixed in which would have carbon, just not as much percent-wise. So adding water to this thing, even though it seems like, yeah, that will increase my overall mass, which then decreases my percent carbon. But as I point out in the little thing here, is that it's kind of confusing because the scientists, nothing wrong with the chemist's technique. He's testing carbon, no problem. So we're trying to say of an actual molecule that has carbon, what would be the one that would be one that is lower in percent mass carbon? So this guy is the same. That's why I X'd that one out. This doesn't have carbon, so it's gone. This guy, unless you scratch it out, to me, I know this answer because you take a glucose molecule and a glucose molecule, you get sucrose, and of course there's a dehydration reaction which you lose a water molecule. So we have all the carbon and we have a little bit less mass, so it's got a little bit higher percent mass. For that case, this one will end up being a little higher, not a little bit lower, which is what we're looking for, which is why this guy is the right answer. Other than scratching out some math on this thing, which would be perfectly fine, all you just do is add these things up and just realize the ratios. I think this is what they're intending, is that you know it's a dehydration reaction. Silicon crystals are semiconductors which are following correct reason for increasing conductivity of silicon crystals with a small amount of silicon replaced with those of a different atom, a different element. So again, silicon is a semiconductor, and which of the following is a correct reason for the increase in the conductivity of silicon crystals when a small fraction of Si atoms are replaced with those of a different element? In this case, of course, silicon being a metalloid has unique properties. The answer here is phosphor atoms introduce additional mobile negative electrons. Germanium would be something that is very similar to silicon, so really isn't going to maybe change as much as if we add something else that is of different property. But this is the actual answer that was given on the exam. N2, molecules absorb ultraviolet light but not visible light. Okay, iodine molecules absorb both visible and ultraviolet light. Which of the following statements best explains the observations? Of course, we're looking at electrons just bouncing up and down, and this is between energy levels. N equals 1, N equals 2, and if you look through it, C is by far the best option. Visible light does not produce transitions between electronic energy levels of N2 molecule. It does produce transitions in the I2 molecule, so it's just talking about going up and down. Here we have a picture of a nitrogen molecule being tested by photoelectron spectroscopy, and they're saying we have basically the energy needed to remove the 1s electron. So they're saying this is the first one, which is the best accounts for the peak of the upper spectrum versus the peak of the lower spectrum. They're the same size, so they contain the same number of electrons, and they're saying in the problem that they're actually the same electron. but this one is farther to the left, which means it's got higher energy. And why? Because in this case, the nitrogen atom has a smaller nuclear charge, which is saying why it's more to the left. It has smaller Coulombic attraction, smaller ionization energy. And that is the end of just some sample multiple choice questions.